turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to the Naked Scientists podcast. This is the programme that brings you the biggest breakthroughs and talks to the major movers and shakers in the worlds of science, technology and medicine. I'm Chris Smith. And coming up, new DNA evidence helps to free a British man after 38 years in prison. Also, Cambridge scientists push up breast cancer survival rates and cut side effects with a new treatment regimen, and why the near and far sides of the moon are worlds apart when it comes to appearance. And it's all down to temperature differences inside, apparently.
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
First this week, a British man who spent nearly 4 decades in prison for a murder he always said he didn't commit has had his conviction overturned by the Court of Appeal. Peter Sullivan was jailed in 1987 for the killing of 21-year-old Diane Sindel in Merseyside. But now, new DNA evidence has cleared him, revealing someone else's genetic material at the scene. We thought this was an ideal opportunity to learn a bit more about the science of DNA forensics, and Churi King, who's a world-renowned geneticist and an expert on forensic DNA at the University of Bath, has been examining the case for us. I began by asking her for a reaction to the new story.
Well, gosh, I mean, what a tremendous miscarriage of justice, really. And as a geneticist, a bit alarming as to how long they've taken to bring DNA evidence to bear on the case, really.
When we approach a case forensically and use DNA, how does it work?
What we're doing is that we're looking at little sections of our DNA that we know vary between individuals, and they're quite variable. So they're very, very good for distinguishing people from one another. And that technology has been available. So the very early days of it were sort of 1984 when DNA fingerprinting was first invented, but it required large amounts of DNA. But since then, technology has been moving on, and it's now possible to use quite small amounts of DNA to be able to determine whether or not a DNA sample comes from a particular individual or not.
Given the ubiquity of DNA and the sensitivity, as you're saying, of the techniques now, how do we make sure it's safe as a technology, though?
That is a really important question. So it starts right from the crime scene in terms of collecting evidence, and this happened in 1986. So very, very early days of being able to kind of sample for this sort of thing. You're worried about contamination with the DNA from another source, such as the person who might have been collecting the DNA. And I understand that they've ruled that out. And I think the other thing that's really important to say about genetic evidence is it's never taken in isolation. You have to take it alongside good old-fashioned police work. It's a strand of evidence that you bring to bear on the case.
How far back can we go with it? So in other words, if you've got a sample, potentially a forensic sample, how long can that lay in an evidence locker and you could get that out and say, I can get a DNA signature from that and I can therefore prove that this person did or didn't have anything to do with a particular crime?
So it all depends on how it's stored. So DNA degrades, and heat and water, moisture, those are the sorts of things that degrade it. But if something's frozen, so there's a really lovely case, it was around the Golden State Killer case, a chap in California who'd been committing rapes and murders. And one of the samples that helped break that case was one that had been stored in a freezer for nearly 40 years. And they were able to go back and get a really good DNA sample from it, and they could use that. I have to confess, I don't know what the time limits are, but I can tell you it will absolutely depend on how it's been stored.
So why do you think, going back to what we've been discussing, why has it taken so long to look again at the present case, given how long this poor guy, Peter Sullivan's been locked up?
I am really surprised. Why has it taken this long? Because we've had really good technology around this in terms of doing DNA testing. So, the National DNA Database was set up in 1995. So we've had various kind of kits that can be used for this for decades. I mean, the one that's used now, called DNA 17, has been available since 2014. I don't know why they've taken so long, because the technology has been around to do this for quite a number of years now.
Now, given that it has exonerated one person, that means that this case doesn't have a suspect now. So can DNA actually help there? Because you mentioned there is a DNA database. People's DNA, when they've committed a range of crimes, are just added to that, aren't they? So is now the approach that you go to that database and start just trawling to look for any matches or hits? Is that how it tends to work?
Well, so yes, I mean, my understanding is they've done that already with the DNA profile. They've had a look on the National DNA Database and they haven't got a hit. So they haven't got a match. But there's other methods that can be used. So there's something known as familial DNA searching. This is because you inherit half of your DNA from each of your parents. The little genetic variants that you've got, you'll share some of those with your siblings or aunts or uncles or this kind of thing. It's usually parents, children, or siblings that they look for. But they could do a search and go, is there anybody matching on this database that looks like it could be a close relative of the perpetrator? And my understanding is that they've done a sweep, so they have screened over 250 men who were suspects originally to see whether or not they're getting any DNA matches there. And of course, for me, given the work that I do on this television program called DNA Family Secrets, is there's the possibility of forensic investigative genetic genealogy, but it's not something that's allowed in this country, but it is allowed in other countries.
And you sort of predicted or presaged my question, which was, it's been very en vogue in the last 10 years or so to find your family tree and send off samples of DNA to commercial entities who will then read bits of it for you. So there are now huge databases internationally of people and their families out there. Could some of this actually be used? Could those companies, if they've got the right legal rights, let's say, could they just offer them to the police and say, would you like to borrow our database to trawl through to look for crimes? Or can that not be done with the samples and the data that they have?
So there's a few things here. So the first of them is, how good is the DNA sample? Because the genetic variation that you look at with DNA fingerprinting is different than what is used for these companies. Obviously, there's ethical issues around this, because people who take these DNA tests, for companies such as Ancestry and 23andMe, they haven't consented to being part of a forensic investigation. So these companies don't allow the police to use their databases. But there are databases that are available that can be used by the police. So there's a couple of issues in there. Is the DNA of sufficient quality to be able to do the DNA typing that you would use for investigative genetic genealogy? And then what databases can you use to do that? It's something that's not allowed in this country at the moment.
But who knows what the future holds? Thanks to Cheery King there. Cambridge researchers have found that a new treatment approach for aggressive inherited breast cancers can significantly improve survival rates and minimise side effects. They've been studying a new form of the disease called triple-negative breast cancer, which is where the tumour cells don't display receptors for the hormones estrogen or progesterone, or a growth factor called HER2. These cancers can crop up spontaneously, but they can also run in families. In other words, they're hereditary. One example of the tumours caused by the BRCA genes, awareness of which shot up when Angelina Jolie announced that she was a carrier. Historically, all of these cancers have been treated identically, usually with chemotherapy up front to shrink the tumour, followed by surgery to resect anything that's left behind. But many hereditary tumours tend to crop up in younger patients, and for them, the side effects of the chemotherapy can be more severe and even have lifelong consequences. So what Jean Abraham wondered was whether anything could be done to alleviate this. And a chance conversation over dinner one night gave her the insight to try changing the timings of the administration of the chemotherapy drugs. The idea being to deliver a regular 1-2 punch to the tumour, but with enough time between each punch for the body's healthy tissue to recover sufficiently to minimise side effects and long-term damage. And for those people with hereditary tumours, it turns out her findings are a massive game changer.
Our trial, which is called Partner, we're asking the question, are people who inherit the tendency to get triple-negative breast cancer the same as people who spontaneously get this cancer, so without any obvious inherited cause? And we, at the moment, treat them both exactly the same, which means that, in our opinion, we thought they were probably getting more side effects and more treatment than they needed.
How did you structure the trial?
We recruited over 740 patients who had triple-negative breast cancer, either that was non-hereditary or that was hereditary. We decided way back when we designed this that what we call the control arm, so what we think the standard treatment would be at the time, was chemotherapy, and it was only chemotherapy. And then we wanted to add in a new drug called olaparib, and this is a drug shown to be quite successful in people who have the hereditary type of triple-negative breast cancer. And it works by manipulating some of the pathways that help us repair our DNA when it gets damaged. So one of the big problems that we were trying to wrap our brains around was how to combine these, because, of course, all drugs have side effects. And the side effects of the chemo and the side effects of the new novel agent, the olaparib, overlap. And if they overlap, sometimes it means that you can't give them together because the side effects are worse than so bad that you can't give the treatment. And I was trying to rack my brain around how to do that when I was at a dinner, at a work dinner in Cambridge. And I sat next to a chap called Mark O'Connor, who was the head of the DNA damage repair unit at AstraZeneca. He'd done some work in the laboratory looking at exactly that question. How can we combine these agents without causing massive damage? And he found that spacing the drugs, so giving the chemotherapy first and then waiting for 48 hours or more, actually meant that the bone marrow, the place in your body that makes the cells that protect you from infection, doesn't get damaged as much. He'd done this in animal models, and I came back to my team the next day and I said, okay, scrap the designs, we're going to try this. And so we thought it was such a simple change to make, to just space out the drugs in a different way.
And what happened? How long did you follow the people up for? And what were the outcomes?
So we'd planned to recruit over a 5-year period, but then unfortunately we had the COVID-19 problems, and all trials really that were not COVID-19 based were suspended or closed for about 2 years almost. But actually, in a weird way, it also helped us because it meant that we'd recruited most of our patients before that shutdown happened. And so all the patients that recruited just accrued time. And so actually we could not only see if they responded to their surgery, but we could also look at those survival endpoints. And so when we finally came to analyse the two sets of patients, what we found was that there's quite a difference in the results between the two different types of triple-negative breast cancer. The people who get triple-negative breast cancer but don't have a strong hereditary component don't respond any better, either in terms of how much disease is left at the surgical time point or how long they survive. So actually the addition of that drug doesn't make any difference. However, in the hereditary breast cancer patients, what we found was that if you space the drugs out correctly, 100% of our patients are alive at 3 years, in comparison to about 88% in the arm that just got the chemotherapy.
So this tells you if you know what sort of disease a person is presenting with, then you can put them on either with or without this additional new drug, and you can spare a group of people side effects if they don't need it. That means that you're immediately refining the therapy and improving the outcome for those people.
Yeah, currently the standard treatment for both hereditary and non-hereditary triple-negative patients would be to get chemotherapy. And what we're saying is that's probably right for the non-hereditary triple negatives. But actually for the hereditary triple negatives, a much shorter course of chemotherapy plus olaparib can actually achieve as good or better, in fact, survival results and a lot less toxicity. And actually, olaparib is a tablet, so you don't have to come in and have an intravenous infusion, so you don't have to be in hospital. So it's time saving, it's bed saving, and it's cost saving. So there's a lot of wins if we can confirm this.
And if you scaled this up to the burden that is breast cancer of the type that you're interested in here, how many people will this directly benefit?
every year, I would imagine somewhere between 1,100 to 1,200 patients would benefit from this.
In just the UK. So if we then extrapolated that worldwide, that's pretty huge.
It is pretty huge, yeah. I mean, I think breast cancer in women is the biggest global killer. So yes, and even though that subtype is a smaller percentage than the whole, when you scale it up, it's a lot of people. It's probably over 200,000 people.
What a great outcome. Cambridge University's Jean Abraham from Addenbrooke's Hospital there. And those results have been published in a pair of papers in Nature and Nature Communications.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
This is the Naked Scientists podcast with me, Chris Smith. Still to come, why are the near and far sides of the moon so dramatically different in appearance? But first, nuclear fusion could one day give us cleaner and almost unlimited energy. The basic premise is that when two smaller atoms fuse to form a bigger one, they release some energy. But the problem is keeping the extremely hot reaction mixture confined in the right place. If it spreads out too much or loses high-energy particles to the surroundings, this hemorrhage of energy quenches the fusion reaction. It's a bit like stalling an engine. Scientists are trying to surmount the issue by developing ways to create a dynamic magnetic cage that can confine the reaction and the products to keep it cooking. But modelling and creating magnetic fields that can do this is extremely taxing. You almost need a nuclear reactor to power the supercomputer to do the calculations. Now though, scientists in the US believe they found a way to solve it. By using a type of maths called symmetry theory, they've created a shortcut to design magnetic systems that can plug any leaks. And, crucially, they've done it 10 times faster than before. Brian Appleby at the Centre for Inertial Fusion Studies at Imperial College London has been taking a look at the study for us.
Nuclear fusion is a form of nuclear energy in which we fuse or join atoms together to release energy. And this is in contrast to nuclear fission, which is the kind of conventional way of generating nuclear power, in which we split atoms to release the energy. So nuclear fusion is really, it's a sort of a holy grail in terms of energy sources, because it releases much more energy per unit mass than all other forms of energy that are available, if we can actually learn how to do it in a controlled manner in the laboratory.
And what are the stumbling blocks in that regard?
The principal stumbling block from a physical point of view is what we must do to force these atoms to join together and to fuse. But because they're positively charged particles, they tend to repel each other. And what we must do is we essentially must give them enough energy in the first place such that they can overcome this electrostatic repulsion, fuse together, and then release even larger amounts of energy. The way in which we overcome that is we make a material that we call a plasma, a very hot collection of these ions. And the thermal energy in the plasma should force them to overcome this electrostatic repulsion.
Indeed, we know the physics works because we can look at the sun and we know that's doing exactly this. And we've also made bombs that work in the same way, haven't we? H-bombs, for example.
Yep.
So we know the physics is right, but now it's an engineering problem then. We've got to get these things hot enough in one place sustainably so they will overcome the natural repulsion and want to start gluing themselves together.
That is true. I might say that I think a lot of scientists might be slightly insulted if you say it's just an engineering problem. So many of these, what we might think of more mundane problems, are related to the fact that when we make this plasma hot, the plasma itself just tends to want to blow apart. So we have a confinement problem whereby we must actually keep this hot plasma confined for sufficiently long times for the reactions to happen.
And how are people trying to make a sort of cage in that way to keep this very hot cloud of atoms in one place where we can control what it does?
A cage is actually quite a good analogy. We must find some way of confining it. There are many different fusion schemes. Quite a few of the schemes are essentially using magnetic fields to create this cage. And so there's a kind of a whole stable of fusion schemes that fall under the term of magnetic confinement fusion.
The thing is, I would guess that when you talk about a cage, cages have bars and bars have gaps between them. So when we create a sort of magnetic cage in that way, there are still presumably going to be gaps. And when you're talking about things the sizes of atoms, they're pretty small. So presumably you're trying to keep water in a string vest.
It's actually an excellent analogy for this reason. So you've got gaps in your cage, but what we know is there are certain designs which are quite effective cages, and we know how we can set these up such that most of the particles in the plasma will not escape through the cage. However, there is a key process within fusion, which is referred to as alpha heating, which we need to generate efficient fusion schemes. And this is because essentially I've said, you force these ions together and they react and they produce energy. Well, what they're actually doing, so these are two isotopes of hydrogen that react, and they produce a high energy neutron and also a high energy helium nucleus, an alpha particle. The neutron is something that escapes from the system, and that's what we can use to recover the energy from. But most fusion schemes, they want the alpha particle to then stay within the plasma and deposit its energy back into the plasma such that the plasma will stay hot. And so really, whilst many people have solved the confinement problem for the isotopes of hydrogen, ensuring that the alpha particles also stay confined within the system is, say, an additional problem that must be tackled separately.
And what does this new paper do? And what does it do that's different? And therefore, how much of a step forward is it?
So this new paper, it essentially develops a new theoretical method for investigating how it is that we can keep these alpha particles confined within the cage. If you want to design a magnetic confinement fusion system, essentially what you're going to end up doing is doing very heavy-duty computational simulations to understand how our magnetic cage keeps all these charged particles confined within it. And people over the last many decades have developed more sophisticated computer models to do this. The challenge is to make sure that these computer models are sufficiently accurate in terms of the physics that they are representing, but at the same time, the time it takes to run the model on a given computer is a feasible amount of computational runtime. And so this new paper used some advanced theory techniques, also some data science techniques, in order to come up with a model whereby we can accurately simulate how it is that alpha particles will stay confined within a given system.
Is the problem that you have this ball of gas with enormous numbers of extremely hot atoms or ions in there? So each of them you've got to keep tabs on. They're going to collide, and some of them are going to fuse, some are not, and therefore you've got new outcomes to try and keep tabs on and predict. And you've got to have a magnetic field in just the right place at just the right time to cater for all of those eventualities. Is that the computing problem, that to create something that will anticipate that dynamic situation and put the field in the right place at the right time at the right rate, and keep doing that millions of times a second, that is a big problem?
That's essentially it. And really, that's the goal of the simulations, is to figure out what sort of magnetic field we need. But there is such a large number of particles that trying to keep tabs on the precise motion of each individual particle is just an intractable problem. So instead, what we're doing is we're using some sort of approximations that we hope should be sufficiently accurate in order that we can track enough of these particles to understand what they are doing in a collective sense.
And does it look like it's going to make a difference, this piece of work?
With all things in fusion, we have to be relative when we decide, is this a breakthrough or not, or how significant is it? And so it certainly is, a kind of a very solid, reliable and interesting development in the theory. But, all that is doing is it's giving us a new theory in which to develop new computational systems on which to design new fusion schemes. So it is very much just one small piece in the overall puzzle. How long it will take us to realize what effect that will have on, say, practical fusion devices or designs, I think that's something we'll just have to wait and see.
Brian Appleby bringing us up to speed on the fusion field and the recent paper in Physical Review Letters by the team at the University of Texas at Austin. To space now. And one of the biggest questions in planetary science is why the side of our moon that faces us has been extensively resurfaced with lunar lava, producing the so-called maria that give it a relatively smooth appearance, while the far side of the moon, on the other hand, also known misleadingly as the dark side of the moon, nothing to do with Pink Floyd, is absolutely peppered with impact craters. Something must account for why the near side is much more geologically active than the opposite hemisphere. Well, now scientists think they might know. Measurements made from space have determined that the moon's mantle, which is the majority of the material on the inside, is warmer on our side than on the dark side, possibly owing to more radioactive thorium being there. And that might be sufficient to make geological processes like volcanism occur more frequently on our side than on the far side. In fact, as Caltech's Alexander Byrne explains, had the dinosaurs had telescopes, they might even have been able to witness recent lunar eruptions.
One outstanding question with the lunar interior has been the very dramatic difference in the amount of volcanism which has occurred on the near side relative to the far side. We've flown past the far side several times. The first time was in 1959. One of the most striking things was the lack of the black Mare basalt on the surface on the far side. And we've never really understood to what extent that asymmetry in structure extends to depth, how it evolved, and whether it is associated with other important features of the lunar interior.
Because it is a striking aspect of the moon, isn't it? The side that we see, which always faces towards us, is covered in a smoother surface, which we say is because of lava. The far side is pockmarked, like it's been belted relentlessly with all kinds of things. And people are saying, well, why should it have two different faces like that? So what are the current theories as to why it looks different on one side to the other? Why might it look like that?
Well, I should quickly preface my answer by saying that we don't know. There are two hypotheses for how the asymmetry formed. The idea that you had a large impact which redistributed material early in the moon's history. The second hypothesis is that there was asymmetric mantle convection. So the mantle basically circulated a lot more on the near side than it did on the far side spontaneously in its early history.
How have you sought then in this study to try to get underneath what is going on the moon and why, some of the reasons why it might look the way it does?
We've taken data from a mission that flew around the moon about 10 years ago called the Grail mission. This was a NASA mission. It was actually two spacecraft that basically tracked their relative positions. So by taking that data of the relative positions of these two spacecraft as they both orbited the moon, we're able to determine variations in the lunar gravity field. There are two components of that field, what's called the static component. This is the part that doesn't change in time. And then there are what are called temporal variations. And these are parts of the gravity field that actually fluctuate with time. And temporal variations in the gravity field occurred almost entirely due to tides. The Earth exerts a gravitational field on the moon, and that field deforms the moon, basically changes its shape. And that change in shape moves mass around, which then creates a time variation in the gravity field. So if you have a weak layer in the interior, for example, a warm near-side mantle, then that will create an anomalous signature in the lunar gravity field. So what we were able to do, we found an anomalous temporal signature in the lunar gravity field. We found that we're able to explain our anomalous Grail data if the near side half of the mantle is about 100 to 200 degrees Celsius warmer than the far side.
Is it effectively, it's a bit like if I had a material like some plastic and I warmed it up, it would be more deformable when it's warm and less deformable when it's cold. So if you've got this temperature difference, it makes the moon bend a bit more on one side compared to the other. And that's why you're seeing this gravity fluctuation, because one side's bending and shifting more under the influence of gravity.
That is almost exactly correct, yes.
Only almost. So I almost nailed it. But why would there be that asymmetry?
The origin of the asymmetry is still unknown. We don't know how material got redistributed on the surface. But what we can say is there's much more radioactive thorium on the near side versus the far side. Once that thorium is in place, it's very easy to warm up the near side mantle so much that it results in melting and convection of that side that doesn't occur on the far side.
Is this segregating like that and differentiating across towards the Earth side in face because the moon is what we call tidally locked? It always presents one face to us and then the opposite side out towards space. And is that why? Because it's in that one position, things can get drawn to one side and not the other?
Yeah, that's correct. So we don't necessarily need for the redistribution to have happened in the present configuration. What could have happened is material was redistributed, it heated up the mantle. That heating up drove a mass, basically a mass anomaly, and the moon reoriented in response to that mass anomaly. So the present day near side may not have been the near side when the Mare or thermal anomaly in the mantle originally formed. It may have reoriented in the process of tidally locking.
But at the same time, what we've ended up with is a soft side and a harder side, and the soft side potentially might be more amenable to lava outflows, which have resurfaced and smoothed out the side we see, but not the opposite side that's harder.
That is correct. Yeah.
And that's a hypothesis, obviously. Your data suggests that might be what's happened, but how can we test that? How can we find out if that is the reason that will explain this age-old mystery of why the moon looks so weird?
Just to be very clear, what we're finding is that in the present day, there is a near side, far side variation in mantle temperature of about 100 to 200 degrees Celsius. So in our minds, that's very striking and suggestive that whatever process formed the near side Mare 3 to 4 billion years ago is still active today, still present in the deep interior, and the moon may even be sporadically active volcanically. So there was a recent study that found that volcanism may have occurred as recently as 120 million years ago. So the short answer is by detecting this thermal anomaly, we have potentially tied together surface processes with deeper interior processes, and then the next step would be to actually identify the origin of this asymmetry way back at the beginning, whether it's due to an impact or spontaneous asymmetric differences in the amount of convection in the mantle.
The enigma that is the Earth's moon. Absolutely fascinating. That was Alexander Byrne at Caltech. That study has just come out in the journal Nature. Well, now it's time for Question of the Week, and this one's been sent in by listener Zhao, and James Titko has been taking a look.
What happens to the body when you inject stem cells of your own that have been cultivated outside? Thanks, Zhao. We can think of stem cells as baby cells produced within our bone marrow, which have the potential to grow into all sorts of different cells. Depending on the genetics within the stem cell and where in the body it ends up, it might turn into a skin cell, a nerve cell or neuron, or even perhaps a blood cell. Now, some treatments for some forms of blood and bone marrow cancers include going after cancerous cells with a high dose of chemotherapy. These drugs can also kill a patient's stem cells or stop their bone marrow from being able to produce healthy blood cells. This may mean a transplant of one's own stem cells could be beneficial. Here to help me explain further is Tanya Dexter, a haematology registrar and senior medical officer at the Anthony Nolan Institute.
So there are two types of stem cell transplants, one where you use stem cells that come from another person, and they're used in conditions where the stem cell is the problem. So for example, with a leukemia. We can also carry out a stem cell transplant using the person's own stem cells, and that's normally given as a rescue after we have given a high dose of chemotherapy. So we use someone's own stem cells to rescue their bone marrow, and that chemotherapy can be given most commonly for some sort of bone marrow cancer, such as myeloma or lymphoma, or for other immune conditions like multiple sclerosis.
So how do we get the patient's stem cells in the first place?
The patient, they receive a medication, an injection called G-CSF, and this pushes stem cells from their bone marrow into the blood. And this allows us to collect the stem cells from the bloodstream, and those stem cells can then be stored. The patient would normally be admitted to the hospital to receive the chemotherapy that we mentioned before, that will wipe out any of the last cancer or the immune cells that we're trying to get rid of. And then a couple of days later, they will receive their own stem cells, which will have been frozen. and defrosted, and they receive them a bit like a blood transfusion. They go in through a cannula into the vein in the arm, and they cleverly find their little way to the bone marrow.
What happens next?
So it takes about 7 to 21 days for those stem cells to have found their way into the bone marrow, made their home, and started to make healthy cells. And that's when we see what we call engraftment, which is the first sign of the white blood cells, in particular the neutrophils, increasing in the blood. And the platelets also will start to increase, and that tells us that the stem cells are making the blood again.
So, Zhao, we might inject someone with their own stem cells if they have a form of blood cancer where we need to rescue their bone marrow's ability to produce blood cells. They're collected and frozen outside of the body and reintroduced after chemotherapy has been administered to destroy any remaining cancer cells. After a few weeks on average, the patient's blood returns to normal. Thanks to Tanya Dexter, Senior Medical Officer at the Anthony Nolan Institute, for helping us with that answer. Next time, we're answering this one from Darren, who writes in, why can we see the light from the first galaxies? Why hasn't that light already passed us, if it was from so long ago when the universe was smaller?
Why, indeed. And if you can shed some light on Darren's question, or you've got a quandary of your own you'd like us to take a look at, you can have your say over on our forum. That's at nakedscientist.com/forum, or you can drop us a line to chris@thenakedscientist.com. That's it for this episode. Be sure to tune in on Tuesday, though, when we're going to be exploring the hidden world of fungi and why scientists are very worried. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It is supported by Rolls-Royce. I'm Chris Smith. Thank you for listening. And until next time, goodbye.